The night is quiet now, and somewhere above the clouds, a machine older than some of your memories is staring into the dark, folding starlight into numbers. And one of those numbers has made grown scientists go very, very quiet. Welcome back to Pale Blue Drift. If this is your first night with us, settle in, get comfortable, dim the lights if you haven't already, because this is the place where the universe gets small enough to hold, and the day gets far enough away to finally let go of. We make these long, slow journeys through space and science and the strange, unfinished edges of what we know, not to wake you up, but to walk you gently down past the noise of the day into something quieter. So if your eyes get heavy halfway through, that is not a failure of attention. That is exactly what this is for. Tonight we are going somewhere unusually far. Not just in distance, though the distance is almost too large to hold in the mind. We are going toward a small, dim point of light called K2-18b, a planet that most people had never heard of until a telescope built to look at the very beginning of time turned, almost as an afterthought, towards something much closer, much stranger, and possibly much more important. Here is the shape of it before we slow down and walk through every piece. In the atmosphere of a planet more than 100 light years from where you are lying right now, the James Webb Space Telescope found the chemical fingerprint of a molecule that, on Earth, is made almost exclusively by living things. Not a planet with a friendly face drawn onto it by an artist. Not a claim of aliens or cities or signals. Just a chemical. A very particular, very telling chemical, sitting in starlight that took over a century to reach us, carrying a question inside it that no one has fully answered yet. That is the real shape of tonight's story, and I promise you the true version is stranger and more careful, and somehow more comforting than the loud version you may have already seen shouted across a thumbnail somewhere. Let's go there slowly. To understand why this planet matters, you have to understand what kind of world it actually is, because it is not a second Earth. It is not a blue marble hanging in space with clouds and oceans like ours. K2-18b is what astronomers call a sub-Neptune, a category of planet we do not actually have an example of in our own solar system. It is larger than Earth, smaller than Neptune, sitting in that strange gap where we are still arguing about what these worlds are even made of. Some scientists think K2-18b might be a small, rocky world wrapped in a thick blanket of hydrogen gas. Others think it might be something even stranger, an ocean world, its surface covered by a global sea, deep and dark, sealed beneath a hydrogen sky, with pressure and chemistry unlike anything on the surface you are lying on right now. This second idea has a name. Researchers call this class of world a hycean planet, a word built from hydrogen and ocean, describing a world that could, in theory, have liquid water oceans and a thick hydrogen atmosphere at the same time, a combination that does not exist anywhere in our own neighborhood of the solar system. If that is what K2-18b truly is, then it belongs to a category of planet we have never actually seen up close. We have never sent a probe to one. We have never touched the surface or the ocean of a hycean world. Everything we know about it comes from something extraordinarily indirect and extraordinarily beautiful, which is the light itself. Here is where the James Webb Space Telescope enters the story, and here is where I want you to slow your breathing for a moment, because this next part is the kind of thing that is genuinely difficult to hold in your mind without a little bit of awe creeping in. K2-18b orbits its star in a way that, from our vantage point on Earth, causes it to pass directly in front of that star on a regular schedule. When it does, a small amount of the star's light passes through the thin edge of the planet's atmosphere before continuing on its long journey toward us. That starlight does not arrive unchanged. As it passes through gas, different molecules in that atmosphere absorb very specific colors of light, specific wavelengths, like a fingerprint pressed invisibly into the light itself. By the time that light reaches Webb's mirrors, over 100 light years later, it is carrying a message, written not in words, but in the exact shades of color that are missing from it. Webb's instruments are built to read that message. They can take that starlight and spread it out, wavelength by wavelength, looking for the tiny dips and troughs that reveal what kind of atoms and molecules the light passed through on its way here. It is, in a very real sense, chemistry done at a distance of hundreds of trillions of miles, using nothing but patience and light. And in the light that passed through K2-18b's atmosphere, astronomers found signs of methane and carbon dioxide, which on their own were already exciting, because they suggested a genuinely thick, active atmosphere rich in carbon, unlike the thin, hydrogen-dominated skis scientists sometimes expect on this class of world. But it was the next finding that made the story travel around the world in a single afternoon. Buried in that same light was a possible signature of a molecule called dimethyl sulfide and its close chemical cousin, dimethyl disulfide. On Earth, these are not exotic laboratory compounds. They are produced almost entirely by living organisms. Marine phytoplankton, tiny drifting ocean life so small you would need a microscope to see a single one, release dimethyl sulfide into our atmosphere by the ton, and it is part of the reason the air near a coastline sometimes carries that particular smell of the sea. On our planet, this molecule is, essentially, a byproduct of life, drifting up from the ocean into the sky. So when a hint of that same molecule turned up in the atmosphere of a planet over 100 light-years away, a planet that some scientists believe might be an ocean world sealed beneath a hydrogen sky, the implications were not subtle. If dimethyl sulfide really is there, in meaningful quantities, and if it really is being produced the way it is produced here, then the honest, careful, almost unbelievable possibility is that we may have detected a chemical signal connected to life itself, drifting across the galaxy long enough for a machine we built to finally catch it. I want to sit with that sentence for a moment because it deserves it, not because it is proven. It is not. We will walk through exactly why gently in a moment, but because of what it represents. For the vast majority of human history, the question of whether we are alone in the universe was a question you could only ask with your eyes turned up at the night sky and your imagination doing all of the work. There was no instrument, no fingerprint, no light to read. It was myth and story and hope, and nothing more solid than that. And now, for the first time, there exists a real measurement, a real signal, however faint, however contested, sitting in a dataset that at least touches the edge of that ancient question. That alone is worth the quiet feeling settling into your chest right now. Whatever the final answer turns out to be, we have crossed some kind of threshold simply by being able to ask the question with data instead of only wonder. Now, here is where I want to slow down even further, because this is the part that separates a story worth trusting from a story that simply wants your attention for a night and then evaporates by morning. The detection of this molecule was not certain. In science, especially in a measurement this delicate, stretched across such a staggering distance, using such a faint signal, there is a number attached to almost every claim, a number describing how confident researchers are that what they are seeing is real, and not simply a trick of noise, of statistics, of the countless tiny imperfections that creep into any measurement pulled from the edge of technological possibility. The original announcement of this detection carried a confidence level that excited a great many astronomers, but did not yet cross the threshold that the field of astronomy reserves for a true discovery. It was intriguing. It was significant enough to publish, to study, to argue about at conferences. But it was not yet proof, and almost immediately, other scientists, working independently, began doing exactly what good science demands, which is trying to break the result. Trying to find the flaw. Trying to see if the signal survived being looked at from a different angle, with different assumptions, different models of what the atmosphere might actually contain. Some of those follow-up studies found the signal weaker than first reported. Some questioned whether the same absorption pattern might be explained by something else entirely, some combination of more familiar molecules mimicking the fingerprint of the one everyone wanted to find. This is not scientists failing each other. This is the immune system of science working exactly as it should, doubting loudly, testing constantly, refusing to let a beautiful idea become a settled fact before it has earned that place. So where does that leave us tonight, lying quietly in the dark, thinking about a planet we will probably never visit? It leaves us somewhere honest, somewhere unresolved. K218b remains one of the most interesting targets in the search for signs of life beyond Earth, precisely because the story is not finished. More observing time has already been dedicated to it. More light will be gathered. The same instrument that found the first hint of this molecule will look again, and again, sharpening the signal, testing whether it strengthens or fades as more data accumulates. And that uncertainty, strangely, is part of what makes this such a good story to fall asleep to, because it means the universe has not handed us a simple answer wrapped in a bow. It has handed us a genuine mystery, still unfolding, still being argued about by people who have devoted their entire lives to reading starlight for a living. There is something deeply calming about a mystery that is honestly still open, rather than one dressed up to look bigger than it is. The open ones are the ones the universe actually offers us most of the time. Let your mind drift for a moment toward what that ocean might actually look like if it exists at all. Picture a sky above it, not blue like ours, but thick and hazy, heavy with hydrogen, filtering the light of a small, dim, reddish star into a permanent twilight glow. Picture a sea beneath that sky, dark, vast, its horizon curving away under gravity slightly different from your own. There is no evidence of anything swimming in it. No evidence of anything at all beyond a possible chemical trace. But the shape of the possibility itself is enough to hold in your mind as your body slowly lets go of the day. We are not going to rush past this planet tonight. There is more of its story still to tell, more about how this single detection connects to a much larger, much older question that scientists have been quietly building toward for decades. A question about how many places like this might exist scattered across our galaxy, waiting in the dark for a telescope patient enough and precise enough to finally notice them. For now, let the numbers settle. A planet more than 100 light-years away, a molecule that on Earth only life reliably makes, a confidence level that is exciting but not yet certain, a community of scientists still testing, still doubting, still looking again. And you here, wherever you are, breathing slower now than you were when this began, carrying that quiet, unfinished mystery with you as the night continues to deepen around you. The light from that distant, dim little star still making its long, unhurried way across the dark, exactly as it has for over 100 years, exactly as it will continue to, long after tonight is over. And that light is still moving, even now, even as your breathing has probably slowed since we began, even as the room around you has gone a little softer at the edges. It left that small, dim star before most of the buildings you have ever stood inside were built. It has been traveling, uninterrupted, in a straight line through the emptiness of space, for longer than any living memory, carrying inside it the faint chemical shadow of a question we are only just now learning how to ask properly. Let's go back to that ocean for a moment, the one that may or may not exist, because there is more worth knowing about it, and the shape of it becomes stranger and more beautiful the longer you sit with it. When astronomers first proposed the idea of a hycean world, they were trying to solve a puzzle that had been quietly bothering the field for years. We had found, by then, thousands of planets beyond our solar system, and a strange number of them fell into a size range with no matching example close to home. Too big to be a rocky world like Earth or Mars, too small to be a gas giant like Neptune or Jupiter. For a while, these planets were simply filed under an awkward, catch-all label, sub-Neptune, a name that describes a size rather than a nature, the way calling something medium tells you almost nothing about what it actually is. But size alone does not tell you what a world is made of, and a group of researchers began asking a quieter, more patient question. What if some of these in-between worlds were not simply smaller gas giants, but something else entirely? What if some of them had a rocky or watery core, wrapped not in a thin sliver of air like Earth's atmosphere, but in a much thicker blanket of hydrogen, dozens or even hundreds of times deeper than our own sky. And what if, underneath that hydrogen blanket, conditions were exactly right for that core to hold something we did not expect to find anywhere except our own fragile blue world? Liquid water, not a trace of ice, not a hint of vapor, an actual ocean, dark and continuous, wrapping the entire planet, sealed beneath a sky unlike anything above your head right now. That is the hycean idea in its full shape. A planet that is, in essence, one enormous ocean, with no continents interrupting it, no shorelines, no islands breaking the surface, just water curving away in every direction beneath a thick, hazy hydrogen atmosphere that never really clears, because there is no dry land anywhere to interrupt it. If you tried to imagine standing on the surface of a world like that, you would immediately run into a problem, because there would be no surface to stand on in the way you are used to. There would only be sky above, thick and dim, filtering starlight down into something closer to a permanent, heavy dusk, and then, without any clear boundary, a transition into deep water below, colder and darker the further down you imagined going, pressure building the way it builds in our own oceans as you descend past the reach of sunlight. It is a genuinely alien kind of world, and yet the physics required to make it real is not exotic at all. It follows directly from ordinary chemistry, ordinary gravity, ordinary orbital distance from a star, the same basic rules that shaped every planet in our own solar system. It simply combines those ordinary rules in a way nature never happened to combine them here, in our particular corner of the galaxy. And this is precisely why K2-18b became such an important test case. It sits in what astronomers call the habitable zone of its star, that narrow, careful band of distance where temperatures could allow liquid water to exist rather than freezing solid or boiling away entirely. Its size fits comfortably inside the range where a hycean nature is possible. And now, layered on top of all of that, there is a hint, however contested, of a molecule that on our world is a signature of living oceans. Every piece, on its own, is modest. Together, they form the outline of a question serious enough that some of the most careful, most skeptical scientists in the world have spent the last several years trying very hard to answer it properly, rather than simply enjoying how exciting it sounds. And that brings us honestly into the part of the story that matters most, the part where the story stops being simple. Almost as soon as the original detection was announced, other teams of astronomers began requesting the same raw data, the same faint dips and troughs in starlight, and running their own independent analysis on it. This is one of the quieter, less dramatic habits of real science, and also one of its most important ones. A result that only one team has ever produced using only one method is treated as interesting, but fragile. A result that survives being tested by rival teams, using different assumptions, different statistical tools, different models of what a planet's atmosphere might contain, becomes something much stronger. K2-18b's biosignature hint did not sail through that process untouched. Some researchers, re-examining the same data, found that the statistical significance of the detection was lower than the excitement around it suggested, sitting closer to a level scientists describe, carefully, as suggestive rather than conclusive. Others pointed out that the specific absorption pattern attributed to dimethyl sulfide sits uncomfortably close, in terms of wavelength, to signals that could be produced by other, far less biologically interesting molecules, meaning the fingerprint might be smudged, ambiguous, capable of more than one honest interpretation. There is also a deeper, more fundamental caution sitting underneath all of this, one that goes beyond any single measurement. Even if the molecule is confirmed beyond doubt in the years ahead, dimethyl sulfide is not, on its own, unambiguous proof of life. On Earth, it is produced overwhelmingly by living organisms. Yes, but chemists have shown in laboratory conditions that it is at least possible to create small amounts of similar molecules through purely non-biological chemical reactions, under the right combination of temperature, pressure, and available elements. Rare, difficult to produce that way, but not physically impossible. And in science, when something is not impossible, however unlikely, it has to be seriously considered before a molecule can be called definitive proof of anything. This is the honest, unglamorous, deeply important texture of how real discoveries are made. Not a single dramatic headline, arriving fully formed and permanent, but a long, careful, sometimes frustrating back and forth. One team proposing, another team questioning, both sides slowly narrowing the space of what could be true, until eventually, sometimes after years, sometimes after decades, something solid enough to call knowledge is left standing. Scientists working on this particular question have been admirably careful about not overstating where things currently stand, even while acknowledging just how significant the possibility is if it holds up. The honest, current answer is somewhere in between excitement and caution, exactly where good science almost always lives, at least for a while. And here is a strange comfort hidden inside all of that uncertainty. If K2-18b's ocean and its possible chemical trace of life were already fully confirmed, wrapped up, settled beyond any argument, tonight's story would already be finished. There would be nothing left to wonder about, only something to memorize. Instead, what we actually have is a genuine, living mystery, unfolding one careful measurement at a time, with more observing time already scheduled, more light already being gathered by instruments built specifically to look again, harder, at exactly this planet. Let your mind sit with the sheer scale of patience involved in this. Webb was not simply pointed at K2-18b once and never again. It has returned to it, and will continue to return to it, deliberately, methodically, treating this single point of light as one of the most important targets currently available anywhere in the sky. Every additional hour of observation adds a little more clarity to the signal, sharpening it the way a photograph slowly resolves out of static. And somewhere in the coming years, that picture will almost certainly become clear enough to say something closer to a real answer, one way or the other. Until then, it remains exactly what it is tonight, a planet more than 100 light years from where your body is resting right now, wrapped in a thick, hazy sky, possibly hiding a dark, continuous ocean beneath it, possibly carrying, somewhere in the chemistry of that ocean's atmosphere, the faint, unconfirmed signature of something alive. And this single planet is not really the whole story either, because K2-18b did not appear out of nowhere. It exists inside a much larger, much longer effort, one that stretches back decades before Webb was ever launched, a slow, patient human project of trying to figure out, scientifically, seriously, how many other worlds like this might be quietly scattered across our galaxy, waiting in the dark, most of them never to be looked at closely enough to have their secrets read at all. That question, the shape of just how many, and how we even began trying to estimate a number for something so vast, is where the story naturally continues from here, drifting outward from this one distant ocean world toward the much wider, much older search that made a discovery like this even possible in the first place. A search built slowly, telescope by telescope, decade by decade, by people who spent entire careers simply trying to prove that other worlds existed at all before anyone could even begin asking whether they might be alive. That wider search did not begin with a telescope like Webb at all. It began much smaller, much more uncertain, in a time when the very existence of planets around other stars was still an open question rather than a settled fact. And it is worth slowing down here, letting the pace of the story stretch out a little, because the patience involved in this part of the history is its own kind of quiet wonder. For most of the 20th century, astronomers strongly suspected that other stars must have planets circling them, simply because it seemed strange for our own sun to be so uniquely surrounded, while every other star sat alone in the dark. But suspicion is not evidence, and for decade after decade, no one had a method sensitive enough to actually detect a planet orbiting another star. The light from any such planet would be lost entirely in the overwhelming glare of its star, like trying to notice a single candle flickering directly beside a lighthouse from hundreds of miles away. The breakthrough, when it finally came in the early 1990s, did not come from seeing a planet at all. It came from noticing a star wobble. A star with a planet orbiting it does not sit perfectly still, because the planet's gravity tugs back on the star just as the star's gravity holds the planet in its orbit, the two of them pulling on each other in a slow, mutual dance around a shared center of balance. That wobble is tiny, almost absurdly tiny, but it changes the color of the star's light in a very precise, measurable way as the star moves slightly toward us, and then slightly away, over and over, in rhythm with its unseen companion. The very first planets discovered this way were nothing like Earth. They were strange, unexpected worlds, gas giants larger than Jupiter, sitting in orbits far closer to their stars than anyone had predicted was possible, completing a full year in the space of just a few days, scorched by heat far beyond anything the planets of our own solar system experience. It overturned the tidy assumption that other solar systems would simply mirror our own, and it opened the door to a strange and important realization, which is that the universe is far more inventive, far stranger, and far less predictable than our own single example had led us to expect. Those first discoveries were exciting, but painstaking to make, one star at a time, one faint wobble at a time, requiring years of careful, repeated observation just to confirm a single planet. At that rate, finding enough worlds to answer any serious question about how common Earth-like planets might be would have taken centuries. What the field needed was not more patience applied to the same method, but an entirely different way of looking, one capable of scanning enormous numbers of stars at once. That is precisely what a space telescope named Kepler was built to do, and its method was almost stunning in its simplicity once you understand it. Instead of watching for a star's light to shift in color, Kepler simply watched for a star's brightness to dim, ever so slightly, at perfectly regular intervals. If a planet happens to pass directly between its star and our line of sight, it blocks a tiny fraction of that star's light, causing a small, repeating, remarkably precise dip in brightness, over and over, once every orbit, like a clock ticking with a rhythm set by gravity itself. Kepler stared, unblinking, at the same patch of sky containing well over 100,000 stars, for years at a stretch, patiently recording the brightness of every single one of them, night after night, watching for those tiny, repeating dips. It was an almost meditative kind of science, a machine doing nothing more dramatic than watching, and watching, and watching, trusting that somewhere in that enormous, patient dataset, the signatures of entire hidden worlds were quietly waiting to be noticed. And they were. By the time its mission was finished, Kepler had confirmed thousands of planets beyond our solar system, transforming the question of whether other worlds existed into the far more interesting question of what kinds of worlds were actually out there, and how many of them might sit in that narrow, careful band of distance from their star, warm enough and cool enough at once, where liquid water could plausibly exist. That band has a name, one you have likely heard before without necessarily knowing its full weight: the habitable zone, sometimes called with a little more poetry, the Goldilocks zone, not too hot, not too cold, but precisely warm enough for water to remain liquid rather than freezing into ice or boiling away into vapor. It is not a guarantee of life. It is not even a guarantee of water at all, since a planet also needs the right kind of atmosphere, the right kind of history, the right combination of countless factors we are still learning to fully understand. But it is the first, most basic filter, the place worth looking closest, the doorway worth checking first before checking anywhere else. Kepler's patient, quiet census revealed something that still, honestly, deserves a slow breath to properly absorb. Planets sitting inside that habitable band around their stars are not some vanishingly rare exception scattered thinly across the galaxy. They appear to be common, genuinely, remarkably common. Some estimates suggest that a meaningful fraction of all stars similar to our Sun may host at least one planet orbiting inside that careful, temperate zone, which means the Milky Way alone, a single galaxy among hundreds of billions of others, likely contains billions of planets sitting in roughly the right conditions for liquid water to exist somewhere on or within them. Sit with that number for a moment in the dark, however heavy your eyelids have become by now. Billions, not within the entire universe, within our galaxy alone, a number so large that it stops behaving like an ordinary number and starts behaving more like a kind of quiet pressure, gently pushing against the far more human intuition that Earth, and whatever might be happening on Earth, must be desperately rare and precious in a lonely, empty universe. The data suggests something different. It suggests that the raw ingredients for a planet like ours, the size, the temperature, the possibility of liquid water, are not rare at all. What remains genuinely rare, or at least genuinely unconfirmed, is whether any of those countless worlds actually developed something living within them. This is exactly the gap that a planet like K2-18b sits inside, exactly the reason a single hint of one particular molecule in one particular atmosphere could travel around the world in the space of an afternoon. Kepler answered the first half of an ancient question. It showed us, with hard, patient data, that worlds capable of holding liquid water are everywhere, scattered generously across our galaxy, far more abundant than anyone dared assume before the data came in. But Kepler could not answer the second half. It could tell us where water might exist. It could not tell us whether anything was swimming in it. That second half of the question required a different kind of tool entirely, not a machine built to watch for tiny dips in starlight across enormous numbers of distant stars, but a machine precise enough to take the light from one single, carefully chosen world and pull it apart, wavelength by wavelength, searching not just for the presence of a planet, but for the actual chemical fingerprint hiding inside its atmosphere. Kepler told us where to look. It could never have told us what dimethyl sulfide even was, let alone whether a trace of it was sitting in the sky of a small, dim, distant world. That is the telescope we began with tonight, the one currently unfolded in space, patiently gathering starlight from K2-18b and dozens of other carefully chosen worlds, built specifically to ask the question Kepler's discoveries first made possible to even ask seriously. It exists because of decades of quiet, unglamorous work before it, one star's wobble at a time, one tiny dip in brightness at a time, an entire community of scientists slowly, patiently proving, piece by piece, that the sky above your head is not simply full of light and silence, but full of worlds, an almost unreasonable number of worlds, most of them still waiting patiently in the dark, for someone with the right instrument and enough time to finally read what their atmospheres have been quietly saying all along. So that is where the trail leads back to, after all of that history, after all of those decades of watching stars wobble and dim and wobble again, all of it converging, quietly, on this one small, dim, distant world we began with tonight. K2-18b was not chosen for observation by accident. It sits exactly where Kepler's long, patient census said the most interesting world should sit, warm enough, sized right, close enough to its star to be intriguing, and far enough away from ours that reaching any real answer about it requires exactly the kind of careful, painstaking light reading that only became possible once humanity finally built an instrument sensitive enough to manage it. And that instrument is not finished with this planet. Far from it. K2-18b remains, right now tonight, one of the highest priority targets on Webb's ongoing observing schedule, which means more light is still being gathered from it, more hours of starlight passing through its thick, hazy atmosphere, more data slowly accumulating in the careful, unhurried way that real answers are actually built, rather than the instant, dramatic way they are sometimes presented. Every additional transit, every additional pass of this planet in front of its star, adds another thin layer of clarity to the signal scientists first noticed. Some of those future observations may weaken the case for dimethyl sulfide, revealing it to have been a statistical shadow, a trick of noise mistaken briefly for something more. Others may strengthen it, sharpening that faint chemical fingerprint until it becomes difficult to explain any other way. Either outcome would be valuable. Either outcome would be real progress. That is the quiet, patient nature of this kind of science, where the goal is not to protect an exciting idea, but simply to find out, carefully, honestly, what is actually true, regardless of which answer that turns out to be. And Webb is not even the final word in this particular search. Even now, plans are already underway for the next generation of instruments, telescopes with mirrors larger still, sensitivity finer still, designed specifically to look at worlds like this one with even greater clarity. Ground-based observatories currently under construction, with mirrors built from dozens of individual segments working together as one enormous eye, and future space telescopes still in early planning, are being designed with exactly this kind of question in mind. Worlds sitting quietly in their habitable zones, waiting for their atmospheres to finally be read clearly enough to settle questions that remain open tonight. One of these future instruments already has a name, the Extremely Large Telescope, currently rising slowly out of a mountaintop in the driest desert on Earth. Its segmented mirror, once complete, wider than a basketball court, gathering so much more light than anything that came before it that atmospheres like K2-18b's could eventually be studied not just for a single molecule's faint shadow, but for a fuller, richer picture, layer after layer of chemistry stacked together, painting something closer to a genuine portrait of a distant world, rather than a single blurred brushstroke of it. Alongside it, further into the future, sits an even more ambitious idea, sometimes called the Habitable Worlds Observatory, a telescope not yet built, still existing mostly as careful engineering plans and hopeful budget proposals, designed from its very first sketch with one specific goal in mind: to directly image Earth-sized planets around sun-like stars and read their atmospheres well enough to search for the kind of chemical imbalance that, on our own world, only a living, breathing biosphere seems capable of maintaining. That last detail matters more than it might first appear. Life, wherever it exists, tends to leave behind a kind of chemical disequilibrium, an atmosphere that should not be able to hold its current mixture of gases if left alone by simple, lifeless chemistry for very long. Earth's own atmosphere is a strange, unstable balance of oxygen and methane existing together in quantities that would slowly cancel each other out if nothing kept replenishing them. Something on Earth, our tangle of forests and oceans and microbes and everything living, keeps pushing that balance back into its improbable, breathable shape, year after year, without ever needing to think about doing so. Finding that same kind of quiet, ongoing chemical imbalance somewhere else, sitting stubbornly in the atmosphere of a distant world despite every reason simple chemistry says it should have faded away by now, may end up being one of the clearest signs of life we could ever hope to find from this great a distance, clearer, in some ways, than any single molecule on its own, however suggestive that molecule first appeared. None of that exists yet. It exists only as careful plans, patient budgets, engineers slowly designing mirrors and instruments that may not see first light for another decade or more. But it is worth knowing that this entire, quiet effort is still moving forward, one careful proposal at a time, built by people who understand deeply that answers like this are rarely handed over quickly, and are almost always worth the wait regardless. Which means the story we have spent this long, slow evening walking through together is not a finished one. It does not end with an answer. It ends, honestly, the way most real scientific stories currently in progress actually end, with a pause, a held breath, a question still open, still being carefully, patiently pursued by people who have devoted their careers to exactly this kind of quiet, unglamorous, extraordinary work. somewhere above the clouds tonight. Whether it is night where you are or somewhere closer to morning, Webb continues its slow orbit, its mirrors cold and still and precisely aligned, waiting for its next scheduled window to look again toward that small, dim star and the strange, possibly oceaned world drifting around it. The light K218b is sending toward us right now, at this exact moment, will not arrive for many decades yet to come. But the light already gathered, already sitting in careful datasets on hard drives and servers scattered across observatories on this planet, is still being read, still being argued over, still slowly narrowing toward whatever the true answer eventually turns out to be. And maybe that is the gentlest way to end this particular night together. Not with a discovery declared finished and settled, but with a mystery still breathing, still unfolding patiently, honestly, exactly the way the universe seems to prefer revealing its secrets, one careful measurement at a time, never in a rush, never demanding to be understood all at once. If your eyes have closed already, that is exactly where they should be by now. If they are still open, let them rest a little. Let the weight of everything we have walked through tonight settle quietly into the background, the wobbling stars, the dimming light, the thick hazy skies of worlds we will never visit, the small, patient signal still waiting to be confirmed or gently set aside. None of it needs to be solved tonight. None of it needs to be carried forward into tomorrow either. It can simply rest here in the dark, alongside you. Thank you for spending this long, slow stretch of night with us here at Pale Blue Drift. If this kind of quiet drifting through the universe is something you'd like to return to, there will be more of these evenings waiting whenever you need them. More distant worlds, more careful mysteries, more long, unhurried journeys built for exactly this kind of stillness. Until then, let the rest of tonight be quiet. Let your breathing stay slow, and let the universe keep turning gently overhead, patient, unfinished, and for now entirely yours to drift beneath. Good night.